So today we're going to be doing some really hard questions. I've got ZPhysics here to help me. You know a bit more about. Yeah, he knows more of the physics than I do. He's much better at the maths and things. So
I'm not sure about that, but let's have a look.
But yeah, so we've got some questions. These are from the British Physics Olympiad. We're not going to do them all because some of them are really difficult and it would take just far too long for anybody to actually watch. But we've got some questions from the 2022 paper. This is round 1 and this is section 1. So we're just going to have a look at a few of these. The first one I thought we'd look at is H, because it's about a rocket and all physics teachers love rockets. I like Lego, as you might well know. So yeah.
This is a mega rocket.
It is, yeah. And the reason we're going to do this question is because most of the time when we use things like Newton's second law, we have uniform acceleration, constant mass. But this question is about a rocket, which is accelerating up, and as it goes higher and higher, it's losing mass. So we've got a thing where the mass changes with time. So, should we begin? Right, so the first bit then is we've got a rocket of mass, 5,000 kilograms. Fuel is leaving at 50 kilograms per second. It goes down at 2,000 meters per second. So for this, we're just going to answer from some white paper.
The students do exactly the same on the real paper as well. I just really want to mention that Olympiad problems are really, really fun. You should definitely have a go. You will learn so much from the problems. Yeah,
I don't know if fun is the right word, but they're definitely problems. No, but actually they're challenging, and when you get the right answer, it is the best feeling.
I agree.
When you actually get it. So it's obviously like you earn that reward. So let's start with H. So part 1. We want to calculate the thrust applied to the rocket. So what is the force acting up? So for this one here, we're going to use Newton's second law, how the force is equal to the rate of change of momentum. Okay, and this is very similar to, actually we did another video where we looked at the force on the side of a tent, and with that one there we used exactly the same equation, just relating the change in momentum to the force.
Who knew there was a connection between the physics of tents and rockets?
Yeah. So there's definitely a link between the two. Now, the change in momentum is going to be equal to the change in mass divided by the change in time, because we've got 50 kilograms per second leaving, and also it's expelled downwards at a speed of 2,000 meters per second. So initially, that gas is kind of, effectively relative to the rocket, that gas is kind of at zero velocity. And then it's ejected it's accelerated down to 2,000 meters per second. So the change in velocity is going to be equal to 2,000. So then we can just put the numbers in. So the change in mass is 50 kilograms per second times the change in velocity, which is 2,000 minus 0, so that's 2,000. 50 times 2,000 is 100,000. And that's the size of the thrust in newtons. Olympiad problem, not even using a calculator.
I know, perfect, yeah.
Like a boss. Right, so I suppose as well, these questions are difficult. They're challenging, but they're not impossible, are they?
Yeah, absolutely. I mean, all we're doing at the moment is really using A-level physics knowledge. Let's have a look at the second one.
Yeah, let's have a look.
So, find an expression for the acceleration of the rocket in terms of its total mass, m, t, and g. Okay, so we're looking for the actual acceleration. Anytime we're dealing with quite a few forces, a diagram, a picture is worth 1,000 words, they say, sometimes even a mark on the exam.
Yeah, it says on the front actually about, working calculations, diagrams must be shown for full credit. So I think, we know it's important. It kind of helps visualize it for yourself, but, they're giving marks just for drawing the diagrams and following that kind of proper method.
Absolutely. Well, in my diagram, let's imagine the rocket is it's not really a square, a rectangle, but this will do.
Yeah.
A couple of forces acting. We have the force due to its weight, which is mg. Just double checking here, they've called the total mass m. That is the mass of the fuel plus the actual rocket. So that's going to be mg. And then we just have the thrust upwards because we're ignoring air resistance, luckily, because otherwise it gets really, really complicated. Okay, so just double check. There's nothing else acting. I could directly actually applying Newton's law. So MA is the sum of all the forces acting on it. I'm going to take T to be positive, and I'm going to take away mg as the weight, meaning that the acceleration will be just equal to T, T over m, and then I am going to do minus g.
Yeah, that's it. So yeah, F equals ma. That's a nice expression there, really. So
far, so good. See,
again,
not that bad.
Yeah, again, that's the kind of thing that I think we saw in some other examples where we were looking at actually the reaction force of a probe on a planet. That's one of your videos. It's pretty much exactly the same thing, just like forces on an object. So the third part, okay, it's where it gets spicy. So find an expression for the acceleration of the rocket as a function of time. Okay, so this is something that is probably beyond the scope of maybe a normal kind of A-level physics exam question, but it's not actually that bad. So we've got T, G, MR, M naught, T naught, all things that we're gonna use to find A. So I would say, because as it gets higher and higher, some of the mass stays the same. So the mass of the rocket stays the same, but the mass of the fuel decreases with time. But it decreases linearly because it loses 50 kilograms every single second. So what we could maybe write is the mass as a function of time is going to be equal to the mass of the rocket, which is mr, plus the mass of fuel that we had initially. And then we're going to take off the mass of fuel that is lost over time. Now for this bit, basically, at time t equals 0, then whatever this is must be its maximum value. And that's going to then get smaller and smaller until we get to the time where the maximum time we could possibly have is equal to t naught. So if I multiply this by t over t naught, effectively what we're saying is that's the time it's been burning for. That's the total time it can burn. And if we multiply that by that times the mass, that tells us how much fuel has been burnt or combusted. Is it combusted?
I don't actually know.
If it's rocket fuel?
It's quite burned.
Yeah, there'll be a chemist there saying exactly what the process is. And yeah, basically m naught minus that is going to be equal to the mass of fuel left. Hopefully that makes sense. So that's mass as a function of time.
You can see how beautiful this equation is and how well it describes reality in a way, because imagine that t is equal to t naught. All of the fuel has run out. Well, if that's the case, then the t's will actually cancel, leading us to m naught, take away m naught. Those terms will disappear, and we're just going to have the mass of the rocket itself, and we'll probably be in outer space.
Yeah, and basically, this is the mass as a function of time that we can put back into this equation to work out how the acceleration changes with time. So the acceleration as a function of time is equal to the thrust of the rocket divided by the mass, but the mass is going to be equal to mr plus m naught minus m naught t over t naught. And then we're going to take off g from all of that. I suppose as well, just looking at like the units, we know acceleration is meters per second.
Really good point.
G is meters per, A is meters per second squared. G can be expressed in meters per second squared. And here we've got a force in newtons divided by a mass. And a force divided by a mass is also meters per second squared. So we know that all the units kind of work. So I'm fairly confident that could be correct.
Me too. In fact, I'll probably give it a tick, but let's see.
Cool, okay. Now that is correct. So part 4 then, we've now got a calculation. So calculate the time after launch at which the weight of an astronaut on board will appear to have doubled.
So this is such a good question, and it's actually really tricky to pick the value for acceleration here. Imagine that you are an astronaut on this rocket over here. Should we grab the rocket?
Yeah, I'll grab the rocket. Not to scale. The two things aren't to scale. But.
Yeah. So here's our astronaut right over here. Now, if the rocket is producing a thrust, the astronaut will appear to feel heavier because the floor will be rushing up towards the astronaut. So an acceleration of g due to the acceleration of upwards combined with that will mean an apparent acceleration for the astronaut that will feel it as as going downwards, they'll feel G to be heavier. So if we were to plug in just one G here, with the combined effect, that's going to produce overall 2 Gs. Let me show you mathematically. So if what I've just said didn't make perfect sense, don't worry, the maths will.
I imagine it, but like if you're in a lift, and if the lift
Exactly.
was accelerating at 9.81 meters per second up, then you would feel the effect of that 9.81 plus the gravitational field strength of 9.81, and you would feel 2G.
Exactly
so it's a bit
right.
like, yeah, the acceleration is basically 9.81, isn't it? So
Perfect.
that makes sense? Yeah. Unfortunately, I don't know any lifts that do that, but that'd be awesome if it did. That'd be good. That'd be fun.
I think a few years ago, actually, there was a question about the lift, which had a very, very similar function for the mass. I'll have a look after.
Yeah, cool.
Okay, so, right, so we're going to stick G into the left-hand side of this equation. Now, this here will give me TMR plus M naught. Take away M naught T over T naught. And then we get a factor of minus G. Now, let's bring this over to this side. So we're going to have 2G is equal to T over MR plus M naught. Take away this factor here, and we're really looking for this time T here.
Should we go to another bit of paper?
Let's go for another one. You need lots of paper if you're going to be taking the Olympiad.
And when your students have done the Olympiad, they just write on plain paper or lined paper?
Yeah, they just typically write, depending on the preference actually, so both are totally fine.
Cool.
Okay, so shall we just rearrange for this factor? So I'm going to bring basically this whole thing on up to this side. So I'm going to have MR plus M naught, take away M naught T over T naught. Well, this here will then be equal to T, and I'm just going to bring this factor of 2G down here. Okay, so what I'm really looking for is this. So I'm going to say that minus M naught T over T naught will be equal to T over 2G, take away MR, take away M naught. Let's get rid of this minus sign, flip everything. So we're going to have M naught T over T naught. Quite a lot of indices. We have to keep on top of them, no?
I'd say there's a lot of writing involved. Even though there's not many calculations, it's like a lot of... And it's so hard not to make a mistake, isn't it?
Make sure to bring another pen just in case one of them runs out. So what will this give me? This will give me MR plus M naught, take away T over 2G. Now, the next thing would be to figure out T naught, which is the total time at which the fuel is being ignited, combusted, or burned. So the way we could potentially figure out is just using this data. So
yeah, so it says we have 5,000 kilograms and we ignite 50 kilograms per second. So it's basically the fuel divided by the fuel per second to get the total time. So it'd be 5,000 divided by 50, which is 100.
Perfect. So I'm just going to write over here so we don't forget.
Yeah.
So just going to be 100 seconds. And I'm going to do the final rearranging before we can plug in. So this thing here will be equal to brackets MR plus M naught, take away T over 2G. I like that Lewis is already putting numbers into the calculator.
Well, I'm getting ready. Yeah, it's team teaching here, isn't it? Yeah, team teaching.
Multiplied by T naught, divide that by M naught, and this should be it. Well,
so, yeah, do you want to start putting numbers in? If I put them into the calculator.
Sounds good. So this will be MR plus M naught was 5,000 plus 5,000. That's going to be 10,000. Divided by the thrust, which we found, it was 100,000, which is 10 to the 5. Just save us a bit of time. Divide that by 2G. So it would have given me 2 times 9.81. Multiply that by 100 after the bracket. And then we're going to divide by the original mass of the fuel alone, which was 5,000.
Okay, I messed up a bit, but I think I'm back on track. Okay, I've got an answer of 98.06.
06. To a physicist, I'm just going to use 2 significant figures.
I think so, yeah, because we've got like 50 kilograms of fuel, so 98 I think is good.
Let's have a look.
Yeah, we've got the mark scheme here. There we go, 98 seconds. Yeah, and a very kind of similar method. I'll say that the one thing is that if you're not sure, sometimes as a student, if you're doing these to practice, or you're a teacher trying to work out what the students can't quite do themselves, these are good if you know the answers, but if you're not sure, it can be a bit of a leap of where they get that from. But it is worth persevering and like kind of using this alongside your own work when you're practicing, because this is good, but it's not as detailed as like a complete step-by-step guide.
Absolutely. And just every single problem teaches you something, which is exactly how we should approach these Olympiad problems. So what will the next problem teach us?
Let's have a look. Now, this second question is about an aeroplane. I quite like planes and stuff, and it's a nice question about bearings and sort of vectors. I guess it links into triangles. It's actually our second attempt at doing this, because the first time my triangle got too messy. So we're going to do better this time, I hope, I promise. So basically we've got a position of a plane noticed. It's then seen another 5 minutes later, and we want to know how quickly it's moving and then where it's going to be in 10 minutes' time. So for this one, the thing that I think you have to do is to draw a massive diagram. And I think as well, use one of these rare things called a protractor.
What's that?
Yeah, students don't have these in their pencil cases. You might need this in an exam, and there might be a few easy marks for like measuring an angle or something. But what I'm going to do is just draw a big triangle. So I'm just going to put in my sort of vertical down here, like this. I'm going to start just around here, and it says the plane is first seen at 68 degrees at a range of 43 kilometres. And then 5 minutes later, a bearing of 040, and we draw our bearings from vertical. So 040 is 40 degrees, 52 kilometres is 156.
If you're new to bearings as well, as Lewis said, we always measure them just from north, and there's typically a bearing style question in almost every Olympiad every year. But let's see.
Okay, so this is my first triangle. And once we've got some information on it, so the first range is 43 kilometres. The second range is 52 kilometres. And the difference between the two angles, because it was 68, it went down to 40. So that angle there is going to be 28 degrees. Okay.
Seems like the cosine rule already, doesn't it? Like two sides and an angle between them.
That's right, yeah. And we want to know how quickly it's going. And because speed is equal to distance over time, we want to work out this distance that it travels in 5 minutes. So what I'm going to do is I'm going to label these in red. So let's say that's angle A, that's length A, that can be B, and that can be C. This is just for me, so I kind of, when there's lots of A's and B's, I kind of can remember what's what. So that's the kind of picture. If I just write down here, the cosine rule, I would say it's not really needed at A-level physics. You can get an A star without knowing it. But I think it's probably useful to know, isn't it?
Yeah, every once in a while you get a question in which it's a little bit easier to use that. Generally, you could resolve vector into components, but it is given in some exam boards, ICE Teach or CR, and it's one of the formulas given in your formula booklet.
So that's the formula there. I'm going to put some numbers in, just like this. And then when I worked that out, the number I got was equal to 24.5857 kilometres. Okay, I'm just going to write it on my diagram up here as well. So I'm going to keep adding to this. So 24.5857 kilometres. That's not the answer. We want to know the time, sorry, the velocity, don't we, or the speed. So that's equal to the distance travelled over time, which is 24.5857. What are the units we're trying to find? Is it metres per second?
Let's have a look.
The question here. Speed of the aircraft in metres per second.
Yeah.
So I'm going to multiply that by 1,000, divide it by 300, because that's 5 times 60. And then when I actually did that earlier, the speed I got was equal to 82 metres per second. So that one over there, speed equals distance over time, and just the third side of a triangle. So
I think we're off to a flying start.
Very good, very good. Right, the next bit then, it says the plane, it's kind of moved this far in 5 minutes. Where's it going to be 10 minutes later? So I'm going to go back to my diagram, and I'm going to extend it to say, okay, so if that's what it did in the first 5 minutes,
Yep. So now
Okay, cool, yeah,
it's
that's it.
10 minutes after that.
Yeah, 10 minutes after that, it's going to be twice that distance. That's about 8 centimetres. So I'm going to extend this by about 16. Again, it's not 100%, it's not a scale diagram. Could we have drawn a scale diagram to, like, I suppose we...
That's when you started doing that with the protractor, I was thinking, can we just skip all the calculations and just measure with the protractor?
I mean, I don't know. I don't think it'd
know.
be accurate enough, but it'll definitely give you an indication of roughly what the right thing is. Now,
We can check at the end, actually. It'll be interesting.
We'll try that. Okay, so we don't know that length, which we want to find out. We don't know this angle that we want to find out. We don't know that length.
And those two angles
Or
as
that
well.
angle, or that angle. Okay,
There's
so
quite a lot we don't know.
But looking at this triangle, if we know this angle and all the lengths, we can work out this one. So I'm going to label that as angle C. Okay, so if we know this length and that angle, and this length, and we don't know that angle, we can use the sine rule. So I'm just going to write it down under here to say that A over sine A is equal to C over sine C. Is that right? That looks about right, doesn't it?
Yep. So A over sine of A is equal to sine C, and then the opposite angle. Yep. Totally
So that
fine.
means C is going to be equal to inverse sine of, so that comes up there. Then we've got C over A times sine A.
Yep. Spot on.
So that's going to be equal to sine to the minus 1 of C over A. So that's 43 divided by 24.5857 times sine 28. Okay, there's a lot there. Let me just work this out in the calculator. This gives me an angle equal to 55.19. I'm going to, again, label it on here. So this is equal to 55.19 degrees. But we want to know this angle in here, don't we? And therefore, that's 180. So if we have 180 minus that, this angle here is 124.8. Okay, so we're starting to know some stuff. What else do we know?
We don't really know that much about. Well, we also know that the distance from here to here is
twice that.
Twice that, isn't it? So we can put that in.
Yes. So the plane was going at a certain speed for 5 minutes. In twice that time, it will have gone twice as far. And this length here is 49.17. I'll leave it like that. So we know this angle. We know that length, and therefore we could use the cosine rule to work out this length.
Yep, absolutely spot on.
So I'm going to relabel some of these things. I'm going to use this colour here. So I'm going to label that length B, and that means this is angle B up here. I'm going to label this side A, so that's angle A down there, and then this is length C, so that's angle C in there. Again, we don't have to do that, but I think it's just nice to sort of show what they are. I'm going to be using even more paper. We have paper everywhere today.
Make sure to have plenty of paper if you're taking the Olympiad.
So let's look at C. So we can say that C is equal to the square root of B squared plus A squared minus AB cos C. That's a bit kind of the wrong order, but you get the idea. We'll put the numbers in, and that means C, when we actually calculate it, is equal to 89.67. So that's a distance from here to here in kilometres, which is kind of 43, 53, 90. That looks kind of roughly right. And we want to know
the bearing, don't we?
Yeah, so we want to know theta, but we can't do that directly.
But we can figure this one out.
Yeah, that's true, because if we know that from here to here is 40 degrees, from there, and we take off this angle A, that will equal theta. So to work out A, we can just use the sine rule. So we could say that A is equal to sine to the minus 1 of A over, should we do B or C? Let's go B. So A over B sine B. I think that's right, isn't it?
Let me have a look at the diagram as well. Ooh, hang on. Plane is away.
Yeah, I think that's good.
Yeah.
Yeah. So that's equal to sine to the minus 1 of A, which is 49.19, divided by B, which is 52, times sine of B. Oh, have I chosen the one that we don't know? Yeah. Okay, so we don't know B, so we'll have to use angle C. So let's say that's equal to C over sine C. So this thing on top here is equal to the distance that we just worked out. So 89.67 times sine of 124.8. Okay, so we've got A and C.
Yep.
Okay, it's a little bit messy, but this is real life, isn't it?
Yeah. Such as Olympiad problem solving.
And when we do that, we find that this angle A is equal to 26.76 degrees. Okay. Looking at this bit down here, though, we want to find theta. And theta is just going to be equal to 40 degrees minus this, 26.76. So therefore, theta is equal to about 13.2 degrees. So that's the angle, and the range is this one up here, so that's going to be about 89.7 kilometres, which I think, let's have a look at the mark scheme, am I right? Okay, they've got a smaller triangle than the one that I did. They've got
89.7 is the range, and a bearing of 13.2 degrees, which is pretty much spot on, isn't it? That's absolutely spot on. Well done.
Yeah, cool. I think, thank you very much. That's a bit of luck. I think partly, though, the reason that question wasn't as bad, although it took a long time to do, was drawing a big diagram and actually using a protractor, not just judging or guessing where 68 degrees is. I think that made the rest of it clear, and constantly going and labelling each length and each angle. And colours helped me. I don't think you don't really get marked down for colours. I don't think it's not like a real exam where they're scanning it.
No, not on Olympiad, I would say.
I think as long as you give your final answer,
or maybe you
in
do have to write on black pen. Just double check what the what it says at the front.
Yeah, double check. If you're unsure about anything, have a look at the Olympiad website, and that'll let you know. Right. So we've done a couple of easy questions to warm up, and now we're going to go on to something which I found particularly challenging.
Oh, let's have a look.
Okay, so the last question we're going to do in this video today is part L. Now, I must admit, I had a go at it. I did a load of stuff, but I couldn't quite finish it. I couldn't quite get the last bit because I forgot about cos and tan and some sort of trigonometric identities and stuff like that.
They're easy to forget, but also they're very easy to look up.
Yeah, and I just didn't have any. I just didn't look them up properly, and it's been a while since I've done that. But this question here, I thought was a really nice question about forces. Yeah, do you want to introduce it? So,
surely at some point you've wondered about the balance between your spoon and your cereal ball. Well, the question, we've got a thin rod which is balanced on a smooth hemispherical ball fixed to a table. There we go. Touching the interior as shown. The rim of the ball remains horizontal. Expressed in the simplest form, determine the radius r in terms of the length of the rod, which is L, and then the angle to the horizontal. It's the sort of thing that I'm definitely wondering every time I'm eating cereal in the morning, so now I get the chance to actually talk about it.
I would say that this looks quite a simple question. You've got like a hemisphere, you've got a thing in it, there's it's a smooth bowl, it says, I think.
Yeah, it is. Yeah.
So that means there shouldn't be any frictional, like horizontal kind of frictional forces. But this one here, I think, is a lovely question, and even if, like me, you didn't quite get to the full answer, but the very act of doing it will have made you just recall everything you know about moments, about forces, about some kind of geometry stuff. So here we go.
Well, let's have a crack.
Yeah. So how do you want to begin?
Probably the first thing would be just to identify what sort of forces are acting on the thing. So we're going to have a bunch of normal forces which are acting. Well, two of them. We're going to have one right here. Anytime that the actual rod is making contact with the ball, there's going to be a normal force. And the direction of that will be at an angle because, well, it's curved. So right over here, we're just going to have a perpendicular component right at the edge, right at the rim. So I'm just going to draw that kind of here. And this one here will be, should we just call this one N2? I kind of want to call this this one N1.
Okay, going from left to right.
Going from left to right, yeah. It just felt wrong calling
No,
it
I
N1,
know.
yeah.
I did exactly the same. Yeah.
This one here will also be at an angle. So, well, I'm going to call this one here, surprise, surprise, N1. Okay, well, this here will have its weight. We'll give them the length of it. And at exactly L/2, assuming smooth mass distribution, we're going to have the weight, which is going to be acting straight down. That looks about L/2.
Yeah, I think so. Yeah, something like that.
So let's just draw our vector, which is just going to be essentially the mg vector. Those problems are typically done by resolving the forces along their horizontal and perpendicular components. We're going to see that N2 seems to act basically perpendicularly. Our next step would be just to consider the angles. So if this angle here is theta, well, geometrically this one here will also be theta. If we were to extend this, kind of like reaching the center, my diagrams are a little bit rubbish. They're not as good as Lewis' diagrams by any stretch of the imagination. It's more of a curve, this, isn't it?
I think, yeah, that's so N1 is basically pointing towards the center of the bowl, as you can see.
Yeah, so basically a bit of space-time curvature in my diagrams, but this would mean that this angle here is also theta. Okay, well, in terms of the forces which act, let's resolve mg along the component, because this force here, component of this force, is keeping it in place. I'm going to say that N1, the adjacent component of this angle theta, is just cosine theta. It better be equal to mg sine theta. You can always resolve mg into horizontal and vertical components. A good rule of thumb to remember is that the angle that the whole thing is inclined at, the sine of that angle is actually the component of the weight along the actual inclined plane.
So the first thing is very much, because it's an equilibrium, we're looking at saying there's no resultant force on it, and that means effectively the force going up the, I suppose it's a rod in this, so basically the force going up the rod, or parallel to the rod, is equal to the force going down the rod, going parallel to the rod down.
Yeah,
so yeah,
exactly
so
right.
Force up, force down, and this one here, N2, because that's at 90 degrees to the rod, will have no component in that direction.
Absolutely spot on.
Cool.
Okay, now I think it's probably time to consider some moments. We can take a moment to consider the moments. I'll stop at some point.
It's all this talk he has.
Okay.
Only we find this funny. Cool, right.
Brilliant, yeah. Okay, so, right, where was I? Okay, considering the moments, N2 we can basically ignore because that's just acting straight right at the pivot point. So I'm not really going to be considering that too much.
So we're taking moments a bit basically around this point here. So there'll be a weight down, and there'll be the force of the bowl pushing up, and they're the kind of two things. Yeah,
exactly.
Cool.
It's really nice when you're writing an equation, somebody just demonstrates what you're doing. Okay, so the force N1, what sort of a moment is going to have? Well, there's going to be some distance away from this point here, and I'm just going to call that, I've got lowercase l, I'm just going to use capital L on this one. This length here, okay, so now I'm going to need to use the force, which is actually trying to make it turn. The force along the length is, well, making it kind of slide along this length, but the moment, that's the force that's causing rotation. So I'm going to use the other component, which is just going to be the sine component. Okay, so I'm going to say N1 sine of theta multiplied by this distance here, L, will be equal to the weight will also have its perpendicular component, which is going to be mg cosine of the angle. The distance between it is a little bit more complicated, and this is where you can see why my messy diagram is not as good. But if this distance here is L, and then L over 2 is the exact position where this is. Oh, I can use a different color, I suppose.
Yeah, colours help.
Colours do help.
People ask me about the pens I use sometimes. They are the Pilot V sign. I think they're great for this, like big scale. Not so much useful for like maybe writing normal notes in class, but when they write, they do write nicely, don't they?
Yeah, they're excellent. It's the first time I've used them.
Yeah, they come in 6 colours. Brilliant. Yeah, okay.
So I'm just really looking for this distance across here. Well, what would this distance be? If L over 2 is the distance from here to the, well, center of mass, then this distance, basically that over here is just L, then this is just L minus L over 2. Okay, well, I can just write this down as L take away L over 2. Now, I've done problems like these before, and I can tell that we're going to have to use the tangent component because it appears in circular motion quite a lot. Mm-hmm. I can take the first equation, and all I'm going to do is just say that N1, because N1 appears here, if I can find an equation for it, I can directly plug that in here. That's just going to be mg sine of theta over cos. Okay, bringing this onto the other side, what do I get? I get mg sine over cos, that's going to be sine squared. Sure, I just write it all out. So this is going to be sine squared. I'm just going to put brackets because I can never remember where to put this,
yeah.
funnily enough. Divide that by cos theta. The cos will also be squared because I'm going to bring this onto this side of the equation. Multiply by L. Well, this thing here will just be equal to mgl minus L over 2. I'm going to use a different color because for some reason I enjoy kind of cancelling things out in a different color.
I know what you mean.
Yeah.
yeah. So we cancel the g's because they're on both sides.
Sine over cos.
So so this is something that, and you can actually do it from SOHCAHTOA as well. If you think about, if you've got opposite over hypotenuse divided by, so if you have opposite over hypotenuse divided by adjacent over hypotenuse, the hypotenuses cancel, then it's opposite over adjacent. So sine over cos is equal to tan.
Absolutely. So we can just write this as tan theta squared multiplied by L is just going to give me L take away L over 2. Okay, now...
I think that's where I got to. And then I thought, okay, so we know the total length is lowercase l, but how on earth do we get to L? And it took me a while of looking at the diagram, maybe drawing it again, where I thought, okay, this is actually how we can calculate big L in terms of theta and some other parts of that.
I think one of the keys here is, especially after you've done quite a bit of algebra, is just to kind of stop and look what you're looking for in the question. In this case, we're kind of looking for an expression of the radius r, but we don't really have an expression of r in this case. So one of these quantities hopefully should depend on r. L, that's not going to really, shall we have a look at, see which one of those depends. So we're looking for r in terms of the rod length, sort of lowercase l. So we can see if we can find an expression for the uppercase L. Should have called it something else, I think.
I think it's clear enough. That's different to that one. Yeah, cool.
Okay, well, how are we going to find that? So what we really need to do is establish a relationship between L and what we're looking for in the question, which is r. Probably the easiest way would be to... Can I just grab that ruler for a second? I think if you consider this triangle, because this distance here is 2r. Why is that? Because this here is the radius, this here is the radius. I might even get a third...
add some more colours to that diagram.
More colour. This is becoming like a work of art here.
Well, sorry, I mean, yes, it is, yeah.
Okay, so we're going to consider this triangle here. Just like that. Okay, so this whole distance here is 2r. The distance here was L, like that.
Yes, that's L.
And, okay, we can just use cosine because the cosine, I might just switch color here, the cosine of theta is going to be the adjacent, which is 2r. The adjacent is L, isn't it?
Yeah.
Divide that by the hypotenuse, which is going to be 2r. Okay, well, if that's the case, L will just be cosine of theta multiplied by 2r, which for some reason I just have to write as 2r cos theta. Because
No, I think that makes sense.
Yeah.
Leave the theta at the end, definitely. Yeah.
Otherwise, I can get confused whether that's in or not. Okay, cool. So I think we're pretty much in business. Let's have a look. So tan of theta squared is equal to, that needs a bit
Is
of
that
tidying
tan
up.
squared theta? Is that how you write it?
I think so, yeah.
Is that how you write it? Or put it in a bracket.
Yes, put it in a bracket,
Yeah, put it in a bracket.
Yeah, I'm sure people will let us know in the
So I
comments
think
below.
tan theta squared, although it's tan theta all squared,
Yeah.
that's different to tan of theta squared.
Yep.
Does that make sense? Yeah.
Yeah,
Okay.
makes total
Cool, right.
sense. Okay, so this here will be equal to L over L, which is going to give me 1 minus a factor of L divided by 2 capital L. I'm just going to refer to it as capital L.
Absolutely.
Cool. So what have we got next? Then I know that L is equal to 2r cos theta. So I'm just going to say that tan theta squared, there's some brackets here, that's just going to be equal to, this here is a 1. Take away lowercase l, divide that by 2 times 2 is going to give me 4r cosine theta. Okay, now...
That's where I got to. So basically, I had an expression for r in terms of L and theta, but it's not finished. It's a bit. It's not messy, but it's like
totally fine in my books.
I think it's good, but it's like you haven't finished like the rearrangement. You haven't made that thing the subject, and we're trying to find the radius r. So really, we want, I guess, to make r the subject of that equation. So how do we do that? So basically, going from here, how do we make r the subject?
Okay, so what I would do is just express tan in terms of sine and cos. If I was to do that, I don't actually remember the trig identity, but you should be able to derive that relatively quickly, I think. If you're taking an Olympiad, just remember them.
You'll know this. Yeah. Just,
well, okay, so tan is sine over cos, isn't it? So that's going to be sine theta over cos theta, and then all of this is basically squared. So anytime I see a sine or a cos, I'm going to be using 1 plus sine squared plus cosine squared is equal to 1. So that will probably just kind of help me with that. So this here will be equal to 1 minus L over 4 cos of theta. Okay, so let's express sine in terms of cos. So this here will be equal to 1 minus cosine of theta. This whole thing is squared. I'm not going to include the brackets anymore, just because of, well, actually, yeah, I should put it here. Okay, I'll include that.
Yeah.
Okay, so this here will be equal to 1 minus L over 4 cos of theta, and then we're going to multiply the whole thing by cosine theta squared. Okay, 1 minus cos theta squared. This is pretty similar to another trig identity for the cos of 2 theta. So this is quite a lot of algebra and trigonometry, but that's totally fine. Okay, this here is equal to cos theta squared, take away L over 4r cos of theta, and then I have a factor of cos of theta squared. That's get cancelled like that. Okay, I can bring this over to this side. 1 minus 2 cos theta squared, which is actually my identity, so hopefully this is going to end up looking quite nice, is equal to minus L over 4r cos of theta. I'll be surprised if there isn't a mistake at the end, but let's see.
Okay, seems to be doing all right, I think. Stage by stage it looks okay.
Okay, 1 minus 2r. Okay, I'm going to have to look at the trig identity because I don't remember it, but I have the trig identity.
There it is.
Right
here.
here.
Yeah,
very conveniently.
Yeah, that's amazing. Cool. Okay.
Okay, so the identity tells me that 2 times a cos of 2 of the angle is equal to 2, and then take away that. Well, this here, if I multiply everything by minus 1, that will put it into the form that I wanted to. So I'm going to say 2, or I can get rid of this minus sign. 2 minus, hang on, let me just start this again. 2 cos theta squared, take away 1, is equal to L cos theta over 4r. cosine of 2 theta is equal to L cosine theta over 4r. Now the final satisfying step, r will be equal to L cos theta over 4 times cos 2 theta.
Okay, tied up nicely, isn't it? But it's lovely to get rid of the tan theta and the cos and just have it all in terms of cos, and also r on its own. So have a look at the right answer. So I'm sure you're correct. They've got L cos theta over 4 cos 2 theta.
Yep, perfect.
Yeah, so they've got this. So I reckon...
It's amazing how the math scheme has about 4 steps on this, doesn't it?
Yeah, I would say that you get basically 1 mark for some of the bits at the beginning, and basically all of this is like for the last final mark. So it's like that's 5 out of 6.
Wait, is that 1 mark?
Yeah, that's basically... if you get that, you've got like 5 out of 6. To be fair, that's still a difficult point to get to.
Yeah.
And that is brilliant. So
I would not have gotten the final mark, by the way, without this. So
yeah, and that's not normally in your physics data book, is it?
No.
So I think that's more like is that maths or further maths that they provide those?
I don't actually know.
Okay, people just know it.
Yeah.
I've forgotten it. So that was awesome work, fantastic. But I think also that question, if you have a go at this, even if you're not doing the Olympiad, you might not get to the last step, but you will at the very least be considering something in equilibrium. You'll be considering looking at resolving forces, maybe along a plane, looking at where the angles go. You're going to be thinking about moments and how actually a lot of the time moments aren't really to do with things which are moving or rotating, but it's like systems which are completely stationary, but you can use moments to solve this kind of static thing. Also, it does allow you to kind of wonder why your bowl or your spoon sits at a particular angle in the bowl, and there's a reason for that with some science. But by doing that, I guarantee if you've done these questions or you spent a bit of time on them, even half an hour on this, and found it difficult, when you go back to past exam paper questions, they are going to seem so much more straightforward by comparison, and the marks are broken down like step by step. So it's almost like, you sort of train hard, fight easy. If you're doing Olympiad questions, that will really improve the rest of your ability and your knowledge across the rest of physics.
It will also prepare you really well for physics at university, engineering at university, or really any technical course.
Yeah. So ZPhysics, thank you for coming down to the studio.
Thank you very much for having me. Absolute dream to be here.
And thank you for helping me with the really difficult physics that I couldn't do. But we're going to do some more Olympiad questions. These are from, I think, the senior challenge. If you want to find that, we'll put a link up here somewhere in the video on YouTube. But also you can head over to ZPhysics and go and see what he's done there, which is brilliant. So thank you so much for watching, and thank you.
Thank you.